Okay, so I'm going to skip ahead in the notes. We got through the finite fields in my sort of virtual lecture last time. I want to talk about chapter 15. Arithmetic rings. These are rings that have some nice things. And the first thing we'll talk about is integral closure. Now, this is sort of the ring theorist's analog of the notion of algebraic. So, definition 15.1.1, let R inside T. I'm often going to specialize in the case where R and T are integral domains. Actually, yeah, I don't want to do that. Yeah, I'm not probably that. You can do this. You can do the notion of integrality more generally than I'm going to do it here, but I'm just going to do it for domains. We say that. So you know what it means for, if these were fields, you know what it means to be algebraic, right? An element T is algebraic, it's the root of some polynomial coefficients at R, right? What's the analog for rings? Like when your ring may not be a field. We say T in T is integral over R if T is a root of some monic polynomial. Monic is very important. F of X and Rx. And in case you're a little fuzzy on what monic is, monic just means that it's the coefficient of its highest degree term is 1. So F of X has this kind of form. I don't allow, making that first, the constant term of the highest degree term be 1 is actually important. It almost seems like this is kind of contrived. But as it turns out, so let me give you an example here. Example, this is, you guys are going to think this is pretty obvious, I think, but I think it's good to point out. If R inside T are fields, T is integral over R. If and only if T is algebra over R. So if they're fields, the assumption of integrality is the same thing as algebraic, which is good. This is what it collapses to. And you might say, well, Jim, algebraic, I didn't demand monic, but it doesn't matter because in the algebraic case, if the leading term here is A and A is not 0, I can just divide this polynomial out by A and it's got the same roots, right? So, and actually, if I wanted to define integrality a little bit more generality, I could have, instead of forcing 1 to be the coefficient here, I could have just said a unit, and that would have been fine. Okay. Let me give you another example. Let's look at this ring extension here. R is the ordinary integers Z, and it lives inside Z. 5, every element of big ring is integral over Z. In fact, I'll explicitly write what a polynomial is. If a plus b square root negative 5 is in the big ring, this is a root of x squared minus 2ax plus a squared plus 5b. You can check me if you like by the quadratic formula. This works out. A plus or minus square root. In fact, the two roots of this are a plus or minus square root of b radical negative 5. Notice the first term here is monic, or I'm sorry, it's 1, so this is monic polynomial, and every element there is integral. Now, here's something that you might find surprising. If you look at two elements that are integral over a ring, so one of them satisfies a polynomial like that, and the other one might be a root of some completely different monic polynomial, their sum and product is still integral, right? That's not obvious, I don't think. And here's payback for all those times that you had to sit through linear algebra, because this is a groovy little approach here. Let me give you, so what it means to be an integral is it's a root of this polynomial. This can be rather heavy-handed to deal with, right? And so I'm going to give you an equivalent condition of being a root of a polynomial, and I'm going to do it in terms of modules, which is going to help us out a bit. Lemma 15. I'm going to call this a proposition. This I need to promote this to proposition at least because this is powerful. 11.1 4. And here, this proposition can be done more generally. I'm going to do this in terms of domains because it's proof. There's a little technical step that we don't have to go through if it's domains. Let R inside T be domains. And U an element of T. So I've got this extension of integral domains, it's an element U and T. The following conditions are number one, is integral over R. Okay. Number two, there exists a finitely generated R module. There exists a finitely generated R module. A inside T such that UA is contained in A. And I didn't say that here, but I want it to be on zero module because otherwise I can just take a zero module. So what I like this, and here's the reason I like this. Because U is integral over R, that's some crazy condition on there's out there in the depths of some Stephen King novel, there's some monic polynomial that this is a root of. This to me seems like a much more tractable condition. Out there is some finitely generated R submodule, non-zero R submodule A at T, such that UA is in A. Okay, so let's do the easy one first. Let's suppose that U is integral over R. What is this? It means U is a root of some monic f of x in Rx. Right? So in other words, U satisfies some equation that looks like this. So U satisfies an equation that looks like this. U to the n plus Rn minus 1, Un minus 1 plus R1U plus R0 is equal to 0. Agree? Okay. Any ideas? So now we've got to find the module, right? Any ideas what we might do here? In terms of generators, just do this. Right. So let A just be, certainly I think we would have to agree, let's see, this is contained in T because U is contained in T, so all the power of U is contained in T. So we just generate this over R. So what this module A is every R linear combination of these things here, every possible one, right? Notice that UA is pretty easy to see is generated by just, shifting those things, right? But what is UN? R0 minus R1U minus R n minus 1 U n minus 1. Right? And notice that because I've got U, this is redundant because I got U squared, the next one's redundant. All the way up, this one's redundant. I'm left with the R0, but this is certainly contained in 1 U squared up to minus 1. In other words, really, I only need the first n minus 1 powers of U, including the 0th power, right? Which is A. So UA is contained in. Everybody okay so far? Of course, the interesting part is the other direction, right? Why is it? How am I going to take? Okay, so I've got some finitely generated A module, and UA is an A. How in the world am I going to get a monic polynomial? This is like super sexy. Check this out. So let's let our module look like this. So from the other direction, A1, A2, up to A. Right? There it is. And we know that UA is contained in A. Right. So whenever I multiply U times any of these generators, it's a linear combination of these generators, right? So let me take you through a couple of them. UA1, well, UA1 is in here, so it's a linear combination of this crap. So this is like lambda 1, 1, A1 plus lambda 1, 2, A2 plus lambda 1, 3, A3 plus lambda 1n a n. And here my lambda ij's are of course in R. Everybody okay with that? And I can go through this like UA2 also has to be a linear combination of these generators. This is 2, 1, A1 plus lambda 2, 2, A2 plus lambda 2, 3, A3 plus lambda 2n, AN. And I can do this for all of them. Lambda n1, A1 plus lambda n2, A2, lambda n3, A3, lambda n, A. Everybody okay with that? Okay, everybody with me so far? Anybody see where I'm going with this? Matrix. Let me change the notation a little bit. Let's write V vector So I'm going to do what linear algebra lets me do. I'm going to sort of compact this into a sort of a matrix equation. If I call the vector V A1, A2 up to AN, then this system of equations basically translates into this. U times V vector is the matrix lambda 1, 1, lambda 1, 2, lambda 1, n, lambda 2, 1, lambda 2, 2, lambda 2, n, lambda n 1, lambda n 2, lambda n times, well, V vector. I agree. Because this column right here, basically, this column corresponds to UA1, UA2 all the way down. So basically, U times V vector is this column vector here. And if I multiply this matrix by that column vector, that's exactly what I get, right? Because the column is A1, A2 down, so that's lambda 1, 1, A1, lambda 1, 2, A2, etc. Everybody agree with that assessment? And if I call this matrix, I don't know, capital A, this is AV equals is equal to UV. And what does that mean about U? U is an eigenvalue. So is root of well, let me say this. What is the solution of, right? So U should be a solution to this equation. But this is a monic polynomial. So U is a root of a monic polynomial in Rx. That slick little proof right there almost makes the suffering of 3110 worthwhile, right? Because bang, it's monic polynomial, so it's an integral. So that's a fantastic little result. And oh, are we going to reap? It is time to reap. I'm going to read with a bigger font. There, 15.15. There. Let R inside T be domains. If U and B and T are integral over R, so are U plus B and UB. Here's the problem's result. And again, this is just like when we talked about algebraic, but I even think it's a step up from here in the sense that it's not clear. I mean, what's the monic got to do with it? But we see the monic actually kept that in the first part of the proof. It's a little subtle there. The fact that the polynomial is monic keeps this module finitely generated, and the monic spits out of this equation for eigenvalue. And a corollary of that is sums and products of integral elements are integral. Here's the proof. There it's just finitely generated. R modules, non-zero. A, B, and T such that UA is contained in A and VB is contained in B. Now, let me observe, and this is a very easy computation, that first observation is the module AB is also finitely generated. These are not just any modules, because they're submodules of T. It makes sense to multiply things in a certain sense, right? Because A and B are submodules of T. So what is AB generated by? Well, if A is generated by A1 through AN, and B is generated by B1 through BM, then AB is generated by all products AIBJ, right? And that's an easy computation to say. So in particular, if A has N generators and B has M generators, then AB has MN generators or less. Because actually when you multiply them, some of the generators might become redundant. But in particular, this is finitely generated. And notice that U plus BAB, because this is generated by the AIBJ, and so the AI part absorbs the U and the BI absorbs the B, so this is still in AB, and in a similar fashion, this is something. And so there you go. Both products and sums of integral elements are still integral. And so a corollary to this, 15.1.6, if R inside T are domains, then here's the notation. This, I'm going to call this, this is called the foreclosure. of R in integral closure of R in the ring T. What is this? This is just everything in T that's integral over R. This is the set of T in T such that T is integral over R. Well, let me point out first that every element, if that T is in R, it's integral because T is a root of X minus R. So there's that. So this is a ring that contains R, and by definition is contained in T. So this is a subring of T containing R. And this is immediate from the previous corollary because what do you need for this? Certainly this is a subset of T. It's certainly not empty because it contains all of R. So you need it to be a subgroup. And it follows immediately from this that if U and V are integral, and so is U minus V, so you've got the subgroup part. And it's also closed under multiplication by the second part of theorem 15.5. So let me give you kind of some terminology. Yeah, let me give you some terminology, then I'll give you some fun examples. Definition 57. Let R T domains R T is called the integral closure. R T. I've already defined that much. If RT is equal to R, so it's possible that there's nothing in T that's integral over R except for R itself. In this case, if you compute what this is and you get nothing new, then R is integrally closed in T. So figuring out what this integral closure doesn't get you anything other than what you started with, and this, then we say that R is integrally closed in T. If we say T is integral of R, that's the other extreme. When I say T is integral over R, what I mean is every single element of T is an integral element over R. Now, this is a little bit spiritually different than algebraic closure, but here's the terminology. If T is the quotient field of R and R and close. And I'll explore this in a moment. So in the case where T is the quotient field of R, so you're just looking at fractions of R. If R is integrally closed in its quotient field, we say that R is integrally closed. So integrally closed in T specifies what the what that ring that contains R is. When that ring is not specified, it assumes that it's quotient. So here's an example. And I'm so happy that I finally get to do this. So okay, we constructed the algebraic closure a little bit more carefully, but let me be a little sloppy and just intuitively do this just for the sake of an example. Q bar is just every complex number that has that is algebraic with the cube, right? So it's every complex number that's not transcendental. Big field, big field. You can visualize it this way: the set of Zn complex numbers such that Zn plus Mn minus one, Zn minus one, M1Z plus M0, 0, or the Mi's are in Z. So it's just every complex number is the root of a minor polynomial with the integer. We can now construct this. This is called the ring of all algebraic integers. And now I know that this thing is real. Why is that? Because I've constructed the algebraic closure before. So that's out there. That's a big field that contains Q. And now I just take the integral closure of Z in that field. Right? Yes.
Just to clarify, when you say real, you mean like exists, not like real number.
I mean exists. Yeah, yeah. Now, we will see momentarily. Well, let me point out that yes.
Is Z like the little z an element of like Q, or what is that?
The complex numbers. I guess the first thing that I might wonder is this a field? We're going to get a theorem later that shows that it's impossible for this to, when you take the integral closure of the domain, it's impossible to get a field. But let me just, I'll just give you one example of why this is not a field. Can anybody think of something, a complex number that is, now, let me rephrase. Can anybody think of an algebraic number that's not in this? It can't possibly be integral over Z. I would think at least half of you get this.
There's no way of 1/2 isn't.
Yeah, one half, for example. Let me prove this. And actually, I'm going to use this to bootstrap the theorem. 1/2 is not in. Whoops, actually. Let's suppose by contradiction it is, right? That 1/2 is in Z bar. Then you have 1/2 to the n plus n minus 1, 1/2 the n minus 1 plus m1, 1/2 plus m0 plus. Am I agreeing with that? And I like this proof here because it illustrates why mnemonic is freaking important. What's the first thing that we might do here? That's right, face your fears, everybody hates fractions, so let's get rid of it, right? So I guess I could multiply both sides of this equation by 2 to the n, that seems to be the most economical thing to do, just turn this into an equation with integers, right? So I'll do that, multiply this by 2 to the n, and this is, n minus 1 times 2, plus n minus 2 times 2 squared, m1, 2 to the n minus 1, plus m0, 2 to the n. And at this point, the contradiction might jump right in your face. Anybody see what it is?
And even is equal to odd.
That's right. This is even, and this is odd.
Oh, sure.
Right, so you're totally toast. So obvious contradiction. Okay, so what have I established here? Well, I've established that this isn't all of Q bar, right? Because 1/2 is in Q bar, but it's not integral over Z. So for sure, the Z bar is missing some stuff. But I do know it's a ring, which is powerful. Let me ask, yes,
What's an example of an element that is in Z bar but is not in Z? Okay.
square root 2. All 5 complex roots, base to the 5th minus 2x minus 6.
So it's not like just a lattice, essentially.
Oh, good Lord, no.
Okay.
This one, let's see, so if you look at the ordinary primes, the integers, not 0, like 2, 3, or whatever. Every one of these. So in this ring right here, it's just like Z in the sense that all non-zero prime ideals are maximal. There are uncountably many prime ideals in this thing that intersect to any given prime, any given non-zero prime in Z, right? It's a huge, huge mess. And in fact, I kind of spoil it by saying this. The first thing you might ask is, does this have unique factorization like Z does, right? But before you ask that, you should ask, does it have any irreducibles? And it does not. There is no irreducible here. You want to prove that for you? This is fun too.
So there are no irreducibles, but it's not a field.
That's right. There are no atoms. And it's not a field. Yeah, we proved it's not a field because 2 is not invertible. 2 is in there and it's not invertible because there's no 1/2. There are no atoms in here at all. It is rather unfortunately named antimatter domain. It's got no atoms whatsoever. Here is a proof. Suppose pi irreducible. What do I know about said pi? I know that pi is a root of something everybody agree with that? I mean, by definition, is this pi could even this could even be a linear polynomial, but it's root of some monic polynomial, right? Right, okay. Now, a tornado root this is another monic polynomial. How did I get this new monic polynomial? That's right.
You plug in X.
Right. So what can you say about the relationship between tornado and pi? Well, you have to pick out one of these roots. You gotta be a little bit careful, but notice that, there exists a root of this that is square root of pi. And there's your contradiction, because you have pi. Pi is radical pi times radical pi. And neither of these can be a unit, because if radical pi is a unit, then that means that pi was a unit, right? And so there are no irreducibles at all in this ring. Everything factors further, no matter what. That's why this is kind of a mess. Let me give you a couple of theorems here. Yeah, that's a really fun example. And it's also a good example of a ring that's not atomic. It's a rather profound example of that. Okay, here's a couple of theorems. I'm not going to prove this first one yet, because when we get a little bit further down the road, we're going to have better tools to do it with. So theorem 15.8. If R is integrally closed. So implicitly R is a integral domain, and being integrally closed, it's integrally closed in its quotient. Then so is this polynomial ring. So it turns out that the integers, the ordinary integers is integrally closed. That means so is the polynomial ring. Of course, if R has quotient field K, that means for this to be integrally closed, means every element of K that is integral over R is already in R. And the same goes true for this. The quotient field of this guy is rational functions in K. So any rational function in K that's integral over the polynomials is already a polynomial that's in there. Yes.
So did you say Z is integrally closed or Z bar?
Both of them are, actually.
So integrally closed doesn't mean you can't take an integral closure?
That's right. If you take a ring and you take its integral closure, inside its quotient field, then that ring is integrally closed. So you're done. It's a closure operation. There's this problem that I asked you. This terminology was, I guess, premature. I gave you a terminology on your homework called complete integral closure, what it means to be almost integral, complete rings that are completely integrally closed are not closed. It is possible. So when you take a ring and you take its integral closure, then you're stuck. You keep trying to take its integral closure, you're stuck there. It is possible to take a ring and take its complete integral closure, and that's not completely integrally closed. And so you take it again, it gets a little bit bigger. These examples are very hard to construct, but they exist. So, and I will put to rest your question in a moment this way. Theorem 15, and I think it will behoove us to do this. I ask you to do this for completely integrally closed in the homework. We'll do it for integrally closed. Any UFD is integrally closed. And it's a fact. So, let's prove this, right? And that'll answer your question about Z. Z's UFD, integrally closed. This also means that any principal ideal domain, integrally closed, right? Proof. Let R and K be UFD with quotient field K. And suppose omega, and I guess I want this to be not zero, because zero is obviously integral. Okay. I'm gonna put one more caveat there in element two. Okay, so suppose I have a UFDR, got quotient field K. And suppose that I have a non-zero omega in K that's integral over R. I'm gonna write that omega is A over B. Okay, and I'm gonna assume UFD allows me to do this very conveniently. GCD AB is one, because you can factor A and B into prime factors and cancel anything you find in common, right? This is actually, the fact you can reduce that fraction, depends on this being a UFD. Because if A and B were actually in Z bar, where everything keeps breaking down, it's not really clear how to reduce the fraction. All right. Everybody will be so far we can see that. Okay, so this means that A over B is a root of some monic f of x in Rx. So I'm going to write out the equation here. Since it's monic, I have A over B to the n plus Rn minus 1, A over B to the n minus 1 plus R1 A over B plus R0 is 0. Now this is, I mean, there's kind of a theme with the way I proved that 1/2 wasn't in Z bar here. Fractions suck. I'm gonna fix that. And the easiest way to fix that is to multiply this by B to the n, right? So I will make it so. So now I've got that. Any ideas on what might help me at this juncture? I want to do this. Suppose P is a prime in R such that P divides B. Let me point out, I probably should have been a little bit more careful. R must have a non-zero prime unless it's the quotient field, right? But if R equals K, right, then it's integrally closed because it's field. Yes.
Sorry, wouldn't you just be able to take out, like move everything to one side that has a B term and then factor out a B?
Yeah, but then what are you gonna do with it? That's why I factored out a P. Because would you agree that there is at least one factor of P here? Right, because every one of these has a B.
Yeah.
So everybody agree that there's a P here. And there's as many P's here as I want, because that's 0. So I must conclude that P divides A in. Now, so far, your idea would have worked, right? B divides A in, right? Agree? But P is prime. P is prime. P divides A. What is the contradiction? Right. So P divides A and P divides B is a contradiction because of the fact that GCD of AB is 1, which we could do because this was a UFD. Okay. So what conclusion must we draw? What do we assume? We assume that P was a prime dividing B, right? We got a contradiction from that. So what does that mean? No non-zero prime divides B. If you're in a UFD and you have a non-zero element that is not divisible by any prime, what must be true of that element? It has to be a unit. So B is a unit. And omega, which is A over B, which is AB inverse, is in R. So R is integral closed. Actually, you can adjust this proof. This is actually true for a GCD domain as well, more general to the UFD. A GCD domain, as you may expect, any two elements have the greatest common divisor. You can modify this proof and show that in a GCD domain is in closed. And I can't believe that I timed it right. Any questions? Okay, remember folks,